Welcome to qnawire.
We have here a hollow parallelepiped whose walls consist of thin metal plates. And these thin metal plates each have their own individual mass. So the plates at the top and the bottom, which are square plates, they're going to have a mass that's equal to 1 over 10 times the total mass of the parallelepiped. And then the plates surrounding this parallelepiped, so the front, back, left, and right plate, are each going to have a mass that's equal to 1 over 5 times the total mass of the parallelepiped. And there's also a rod going from point A to C prime, and we need to find what the angular momentum is about this point G, and also the angle theta that's in between the angular momentum and the points A to C prime. So we'll start by finding the distance from A to C prime, and we'll call that distance D, and that's going to be equal to the square root of 2 times A squared plus the square root of 2 times A squared. And this will give us a length that's equal to the square root of 6 times A. So next we're going to find the moments of inertia of the square plates, so the top and bottom plate. So square plates. For the x component, that's going to be equal to 1 over 12 times m1 times a squared plus m1 times a squared. And we can plug in m1 and simplify down to 13 over 120 times m times a squared. For the y component, that's going to be equal to 1 over 6 times m1 times a squared. And we can plug in m1 and get a value of 1 over 60 times m times a squared. And now for the z component, I of z, that's going to be equal to 1 over 12 times m1 times a squared plus m1 times a squared. And so we can plug in m1 and simplify down to 13 over 120 times a squared. So now we're going to find the moments of inertia of the plates that are on the xy plane. So we're going to find the moments of inertia of the plate that's in the front and the plate that's in the back. So these are going to be the plates on the xy plane. So for the x component of those plates, that's going to be equal to 1 over 12 times m2 times 2 times a squared plus m2 times a over 2 squared. So you can plug in m2 and simplify it down to 7 over 60 times m times a squared. For the y component, that's going to be 1 over 12 times m2 times a squared plus m2 times a over 2 squared. And plugging in m2 and simplifying down, it's going to be 1 over 15 times m times a squared. And for the z component, that's going to be 1 over 12 times m2 times a squared plus 2 times a squared. And then we can plug in m2 and simplify down to 1 over 12 times m times a squared. So next we're going to find the moments of inertia of the plates that are on the YZ plane. So it's going to be the plate on the left and the plate on the right. So YZ plates. For the x component of those plates, that's going to be 1 over 12 times m2 times a squared plus 2 times a squared. So we can plug in m2 and we'll get 1 over 12 times m times a squared. For the y component, this is going to be 1 over 12 times m2 times a squared plus m2 times a over 2 squared. So we plug in m2 and simplify it down to 1 over 15 times m times a squared. Now for the z component, that's equal to 1 over 12 times m times 2 times a squared plus m2, and this one over here should also be m2, times a over 2 squared. So finally, this component is going to be equal to 7 over 60 times m times a squared. So now what we're going to do is we're going to take all these moments of inertia that we calculated, and we're going to take the summation of all of them for each component. So now we take the summation of the components. So the x component of that moment of inertia, we can write it as 2 times 13 over 120 plus 1 over 12 plus 7 over 6a times m times a squared. And then we can write it as 37 over 60 times m times a squared. So for the y component, we write it as 2 times ma squared divided by 60 plus ma squared divided by 15 plus ma squared divided by 15. And this becomes 3 over 10 times ma squared. Now for the z component, we can write it as 2 times 13 times m times a squared divided by 120 plus 7 times m times a squared divided by 60 plus m times a squared divided by 12. And this component is going to be equal to 37 over 60 times m times a squared. So we now have all the necessary components to calculate the angular momentum about the point G. So the angular momentum about the point G, that's going to be equal to the x component of the moment of inertia times the x component of the angular velocity, and then plus I of y times omega y plus I of z times omega z. So we can plug in the components of the moment of inertia, and we know that the angular velocity is just given as omega. So h of g is going to be equal to negative 37 divided by 60 times m times a squared divided by the square root of 6 times the angular velocity I plus 3 over 10 times m times a squared times 2 times omega divided by the square root of 6 j, and then minus 37 over 60 times m times a squared times omega over the square root of 6. And then we can simplify this as m times a squared times omega divided by 60 times the square root of 6. And since we want to find the magnitude of what this angular momentum is going to be, we write it as 37 squared plus 36 squared plus 37 squared, all under the square root. So finally, the angular momentum is going to be equal to 0.4321 times m times a squared times the angular velocity. So now we have to find the angle between this angular velocity and the distance, so the position from point A to C prime. So I'm going to clear this part out to make room for our calculations. Okay. So what we can do is we can write the angular velocity at point G dot the angular, well, so the angular momentum about the point G dot the angular velocity is equal to the angular momentum times the angular velocity times the cosine of theta, since this is a dot product on the left side. So we can write it as cosine of theta is equal to h of g dot omega divided by the magnitude, those magnitudes multiplied by each other. So now we can plug in. So taking the dot product, we'll get 0.4055 And multiplying the magnitudes, we'll get 0.4, 321. So we can then write cosine of theta. So this is going to be equal to 0.9384. And then we take the cosine inverse of that value. And then we'll get an angle that's equal to 20.2 degrees.